Welcome back to this module on pipelining. The topic of this lesson is control hazards. Control hazards are also known as branch hazards. We have dealt with structural and data hazard. Now let's move on to the third kind of hazards, control hazards, also called branch hazards. Control hazards occur because the processor does not know the outcome of a branch when it needs to insert a new instruction into the pipeline in the fetch stage. In particular, in our current pipeline data path, branches are executed in the mem stage, which means they actually take effect at the end of the mem stage. To understand control hazards, let's again draw a pipelining diagram. You will have noticed by now that pipeline diagrams are very useful to understand what is going on in a pipeline. In the first cycle, this instruction, a branch of equal, is fetched. I assume this branch is stored at address 12 in memory, as indicated by the number 12 in front of the instruction, and the offset contained in the instruction is 5, meaning that the branch should jump to the instruction at the address given by the current PC, 12, plus 4 times the offset 5, and this equals 36. In the next cycle, the branch is decoded, and at the same time, the next instruction at address 16 is fetched. If the branch is taken, which is not known at that time, the instruction at address 16 is not the next instruction in program order. This continues until clock cycle 4, at which time 2 more instructions have entered the pipeline. At the end of clock cycle 4, in the mem stage of the branches takes effect. So if the branch is taken, the correct next instruction in program order is fetched in clock cycle 5. By that time, 3 other instructions have entered the pipeline. So in essence, we have a 3-cycle penalty for taken branches. The first question we should ask ourselves now is this affordable? Is this penalty negligible? This depends on the frequency of branches. A 3-cycle penalty would be terrible, because according to statistics, by average branch takes place every 5 to 6 instructions. The efficiency of the pipeline will be reduced to a great extent. Let's evaluate the performance impact of a 3-cycle penalty on taken branches in more detail. Let's assume the ideal or perfect CPI equals 1. Ideal CPI means the CPI in the absence of control hazards and in the absence of data hazards. We also assume that 30% of all executed instructions are branches. This is high, but not unreasonable. In reality, on average, 1 out of 5 to 1 out of 7, so about 15 to 20% of all instructions are branches. We also assume that 50% of all branches are taken, which is a very realistic assumption. And as stated before, we assume a 3-cycle penalty for taken branches, but branches that are not taken do not incur a penalty. Under these assumptions, the actual CPI will be 1, the ideal CPI, plus 30%, the branch frequency, times 50%, the percentage of branches taken, times 3, the taken branch penalty. This equals 1.45. In other words, having a 3-cycle penalty on taken branches means a performance penalty of almost 50%. This is not acceptable. Because we cannot afford a 3-cycle penalty on branches, we need to reduce the branch delay. Reducing the branch delay involves 2 things. First, we need to determine whether a branch is taken or not earlier in the pipeline as soon as possible. Second, we also need to compute the address to jump to, the target address, earlier. In MIPS, this is done as follows. Both the branch condition evaluation and the calculation of the branch target address are moved to the instruction decode, the ID stage. In order to calculate the branch target in the ID stage, we need an extra adder in this stage that adds the offset contained in the instruction to the program counter plus 4. By moving branch execution to the ID stage, we reduce the branch penalty from 3 cycles to only 1 cycle. Computing the target address in the ID stage is relatively easy and can be done as soon as the branch instruction is fetched and even before it is decoded. The offset is contained in the instruction and PC plus 4 has already been calculated in the previous stage. The branch condition evaluation needs to be done fast, as we first have to read the register file, and the branch condition evaluation should not increase the length of the critical path and hence reduce the clock frequency. In order to be able to evaluate the branch condition in a fraction of a clock cycle, the branches supported by MIPS are relatively simple. We test if a register is 0 or unequal to 0, or if 2 registers are equal or unequal. These tests can be done quickly. MIPS, at least the MIPS1 instruction set, does not support, for example, branch if less than or branch if less than or equal. These branches are more complex and cannot be evaluated in a small fraction of a clock cycle. Now I sketch how the pipeline data path, the hardware, needs to be changed in order to reduce the branch delay. As an example, I will focus on the branch if equals 0 instruction. In the previous data path, the branch target address is computed in the execute state by the red colored adder. The first thing we need to do in order to move branch execution to the ID stage is to move this adder to the ID stage. The input to these adders are PC plus 4, which has been calculated in the previous stage, and the sign extended immediate contained in the instruction. To be 100% correct, this immediate needs to be multiplied by 4, but for simplicity this has been omitted. The branch condition register is evaluated by this block labeled 0 ? It tests if register RS, which has just been read from the register file, is equal to 0. If so, it steers this multiplexer so that it does not select the next sequential PC, which is equal to the previous PC plus 4, but the branch target address. Finally, at the end of the cycle, the new PC is latched into the PC register, and in the next cycle, the instruction at the branch target will be fetched. There are 2 flies in the ointment, however. First, additional forwarding hardware is required because the source operands of a branch comparison may be produced by the instruction currently in the mem stage or the instruction currently in the write-back stage. Second, a stall is required if the source operand is produced by the instruction currently in the execute stage. For simplicity, I have omitted these details in this figure. Some questions still remain open. For example, even if branch execution takes place in the ID stage, by the time the correct instruction is fetched, the instruction following the branch has already entered the pipeline. What do we do with these instructions?